All right, y'all, we're going to do a quick video on 2.7 inverse functions. This is the last section that we'll cover a video on before we meet back together next week, but let's go ahead and go through it. The first thing that we'll do is read through this quick definition of the criteria for being an inverse. And it relies kind of on that function composition stuff that we did a video on last time. Remember, if you need a quick reminder on the function composition stuff, that is just a quick way of showing notation for plugging one function into another function. So for example, in order to be an inverse function, whenever I plug g into f of g of x that is, then you should just get x back. That's one of the criteria. The other criteria is that whenever you do the other composition, whenever you plug f into g, that you should also just get x after plugging that function into each other. If we say that f and g are inverses, meaning they follow these two properties, then we can write g as f inverse. And this is kind of an important note down here as well. The domain of f inverse is the range of f, and the range of f inverse is the domain of f. In other words, the domain and range will flip-flop between the inverses functions. So f will have the domain of f inverse, and f will have the range of f inverse as its domain as well. So you can replace them in that method, okay? Let's look at some examples real quick about how we can verify whether or not a given function is an inverse, and then also use this process right here to figure out what the inverse of a particular function will be. So let's start with example one. Let me try to line this up, there we go. Example one. And we'll first look at verifying that the given functions are inverses of each other. What we're given here is f of x is equal to 3x plus 2. And then also g of x is equal to x minus 2 over 3. Okay. Now what we'll do to verify that these are inverses of each other is verify the two properties that were shown in that definition. Namely, we need to verify that f of g of x is equal to x, so that's one property that we'll verify. And then maybe on the right-hand side over here, we also need to verify that g of f of x is equal to x also, right? If we can verify these two properties, that means that f and g are inverses of each other, okay? Let's start with f of g of x. Well, the g function is just x minus 2 over 3. So to verify this left-hand side then, that's what I'll focus on, is f of g of x is going to be f of x minus 2 over 3, because that is what we are defining the g function to be, okay? Now, let's go ahead and rewrite this. We have f of x minus 2 over 3. We need to plug this is our input, into our f function. So we'll have 3 times x minus 2 over 3 plus 2. And notice that whenever we start simplifying this, the 3's are going to cancel out, and I'll just be left with x minus 2, that numerator, plus 2, and then the negative 2 and positive 2 will cancel out, and I'll just be left with x. So f of g of x is in fact just equal to x, and that verifies one of the properties that we need for this. So we're halfway there. Now we just need to do the other side, and we need to plug the f function, 3x plus 2, into the g function, and then hope that we also get that same cancellation occurring. So let's plug 3x plus 2 into the g function, and we'll get 3x plus 2. That's our input. Minus 2 over 3. Again, remember, the g function is x, so that's our input, x minus 2 over 3. Simplify this where it makes sense to. The parentheses here are unnecessary because we're not doing any distribution or negation. So we can go ahead and drop them, and then we can combine the 2's, and we'll get 3x over 3. And of course, the 3's will cancel out, and I'll just be left with x. So then we have that g of f of x is also equal to x. Since both of these properties hold right here, that means that f and g are inverses of each other. And I'll kind of write that as a summary statement below. Since f of g of x is equal to x, and g of f of x is also equal to x, then f and g are inverses of each other. Okay, wonderful. So that's how to show that functions are inverses of each other whenever they're given to us directly, like we were explicitly given what f and g were for this particular problem. Let's look at a different example of maybe trying to figure out what a function's inverse should be if we're just given the one function. So example 2. A says f of x is equal to 7x minus 5. Okay? Now, I'm going to flash it one more time real quick, but there is a procedure for how to figure out how to find an inverse of a function. It's given to us right here in the notes. And it says that to find the inverse function, first replace f of x with y, interchange x and y, solve for y. If the result is not a function, then that means that there is no inverse function. Otherwise, if we can solve for y without there being any problems, then we can move on to step 4. All right, let's look. Here we have the function. We're going to go ahead and go through that process like we mentioned. First, we'll swap out f of x for y. And now, everywhere where we see a y in the function, we're going to replace it with an x. And everywhere where we see an x, we're going to replace it with a y. So we'll have x is equal to 7y minus 5. And then the final step is to just go through and solve this for y. There's a couple of different ways that you can do this. Maybe I'll just add 5 to both sides and isolate y on the right-hand side. So what I'll get is x plus 5 is equal to 7y. And then what we can do is we can divide both sides by 7. And then we'll get x plus 5 over 7 is equal to y. If you wanted to do a little bit more simplification, you absolutely could, but that's all that you would need to do to figure out this right here. It also says to find any values not in the domain. Notice here for this one that we're not doing any division by 0. There's no x's in the denominator, and there's also no square roots. So we don't have to worry about any possible domain restrictions here. Let's look at b next. B is going to give us the function f of x is equal to 4x cubed minus 1. Okay, we're going to treat this just like we did the other one. First, we'll say y is equal to 4x cubed minus 1. And then we can go ahead and swap x and y. So we'll have x is equal to 4y cubed minus 1. And then we need to solve this expression for y after we get here. Once we have this, we'll go ahead and do that. Maybe I'll add 1 to both sides, kind of like we did last time. So plus 1 plus 1. Whenever we do that, we'll have x plus 1 is equal to 4y cubed. A good step at this point maybe would be to divide both sides by 4. So I'll do that next. Divide by 4. Divide by 4. I'll be left with x plus 1 over 4 is equal to y cubed. And then now I have to get rid of this cube somehow. Just like we were able to get rid of the square with the square root, we have to be a little bit careful because we have that plus or minus issue with the square root. But in this case, we can get rid of it with the cube root. We only need to worry about the plus or minus root on even powers. So that means that for this one right here, whenever we choose to take the cube root of both sides, so x plus 1 over 4, the cube root is equal to the cube root of y cubed. We don't need to include the plus or minus because it is an odd power. Remember, we had this discussion last time, but whenever we talk about odd powers, it is possible to get negative numbers out of them. Whenever we're looking at even powers, you cannot get a negative number out of an even power number, right? So that means that the cube root of y is just going to be y, and then on the right-hand side, what I'll be left with is just the cubed root of x plus 1 over 4. And that would be it. So that would be my equation for y. I should probably go ahead and write f inverse because that is what it asked us to do for the last one. So this is the equation for the inverse, but just to give the actual inverse a name, I'm going to go back and do it for both of these guys. I could call this f inverse of x is equal to x plus 5 over 7. So that would be the actual function notation for that. And I'm going to do the same thing for this one as well. I'm going to say f inverse of x is equal to the cube root of x plus 1 over 4, okay? So we have these two different representations of it. If it's asking for the function notation, it wants you to use this f inverse notation. This equation is all we've gotten just for the equation part, okay? Let's look at a couple more. Here we have C, and we're given f of x is equal to 5 over x plus 4. All right, I'm going to keep going through the same procedure that we did with the last one. First, we'll say y is equal to 5 over x plus 4. Then we'll go ahead and swap x and y. So we'll have x is equal to 5 over y plus 4. And then at this point, we need to do some work to get y by itself. Now, what I would recommend doing whenever you see the variable that you want to isolate in the denominator is to first get everything that is not part of that variable onto one side. So for example, I'm going to start by subtracting minus 4 from both sides, or sorry, subtracting 4 from both sides, adding a negative 4. And what we'll be left with is x minus 4 is equal to 5y. The reason why this is helpful is because now we can choose to multiply both sides of this equation by y. So what I'm going to do is on the right-hand side, I'm going to multiply by a y, and I'm going to multiply the entire left-hand side by a y as well. So what I'll be left with after doing that is y times x minus 4 is equal to just 5, because y over y on the right-hand side is going to cancel out. Now on the left-hand side, notice that the only thing keeping y from being by itself is this x minus 4. So really, the only thing that we need to do at this step is just divide both sides by x minus 4. And what we'll be left with is, I'm going to go down a little bit more, y is equal to 5 over x minus 4. And of course, just like last time, it'll probably be helpful to write this in its actual function notation as well. So we can say f inverse of x, the actual inverse that we found here, is 5 over x minus 4. So that would be the inverse answer right there. Notice that this inverse actually does have a potential domain issue though, right? If I try to think about plugging 4 into this value right here, I'm actually unable to, because if I plug in 4, then that would lead to a 0 in the excuse me, in the denominator. So I need to exclude x is equal to 4 from the domain. So you can make a note of that. You can say x is equal to 4 must be excluded from specifically the domain of the inverse, domain of f inverse, right? Because it works just fine in our original function being this up here, right? The number that doesn't work in this original function, the domain of the original function would be 0, right? Because then you'd be dividing by 0 directly. So you do have to be a little bit careful, right? You're going to have some differences in these domains and ranges for each of these functions. They are the opposites of each other. So this guy's range will be this guy's domain, and this guy's range will be this guy's domain, but you have to make sure that you're keeping them straight within each other as well, okay? Let's look at one more, and then we'll move on. D, the last function that we'll look at is f of x is equal to 2x minus 3 over x plus 1. This will easily be the most complicated one that we'll talk about in this section, so definitely slow down, take notes on this one, because we're going to be going through it. We're going to treat it just the same as we've done the other one. We'll set it up y is equal to 2x minus 3 over x plus 1, and then we'll swap all the x's and y's, so we'll have x is equal to 2y minus 3 over y plus 1. And now at this point, we're tasked with finding the solution to the solved for y, right? So let's go ahead and look at how we might do that. My goal, again, is to try to get all of the y's on one side, particularly all the y's in the numerator on one side. And whenever you have y's in the numerator and the denominator, you want to clear the y's out of the denominator as quickly as you can. Now, what I see here is that if I multiply this side by y plus 1, and I also have to multiply this side by y plus 1 if I choose to do that, that y plus 1 over y plus 1 is going to cancel out, and then I'll be left with y plus 1 times x is equal to 2y minus 3. That's a good step because it immediately clears my y's out of the denominator, and now I just have to work at maybe getting all of my y's on one side. So that's probably what I'll work towards next. I'll distribute this x into the parentheses set, and I'll have x plus y plus x is equal to 2y minus 3. Now I'm going to do a couple of things in this step. I want to get all of my y's on one side and then all of my x's on one side. So what I'll do is on the right-hand side, I'll go ahead and subtract 2y, which means I also have to subtract 2y on the left-hand side. And on the left-hand side, I don't want this x, I want all my y's over here, so I'll subtract x on both sides as well. So I've done two steps, the red step and the blue step. And what I'm going to do on the next line is I'm just going to carry out the consequences of that. I'll have xy minus 2y. X and negative x are going to go away. 2y, negative 2y are going to go away, and I'll be left with negative x minus 3. So all that I've done here is I have chosen to collect all my terms containing y on the left-hand side and all my terms not containing y on the right-hand side, and we will see why that will be helpful for us in just a moment. But I'm going to go ahead and move this back up to right here, just to give us a little bit more room to work with this problem. So again, I have x minus 2y is equal to negative x minus 3. At this point, because you have all of your y's on the left-hand side, you can just factor out a y from each expression on the left-hand side. So when I factor out a y from each of those expressions, I'll just have y times x minus 2, and then on the right-hand side, I'll still have negative x minus 3. Notice that if you distribute this y back in here, you'll get right back to where you started. That lets you know that you've done the distribution correctly, right? Y times x is xy, y times negative 2 is negative 2y. Now, notice we can just divide both sides by x minus 2, and then that would get us y alone. So I'll go ahead and divide by x minus 2, divide by x minus 2, and what I would be left with is y is equal to negative x minus 3 all over x minus 2. That's all the algebra out of the way, because y is isolated, so we can replace that y with an f of x, or f inverse of x, and then we can say that that inverse function is going to look like this right here. Now again, we might want to note the domain restriction here because we can't divide by 0, so that means x cannot be equal to 2. So we'll say x cannot be equal to 2 for f inverse. All right, wonderful. Again, that was the more complicated one out of the inverse functions that we found so far. But if you feel confident with that one and the other ones that we've done, you should feel confident solving for inverses in general. Okay, let's look really quickly about how we can tell whether or not a graph will have an inverse, a function will have an inverse just by looking at its graph. Okay, that's going to be this next blurb. It says we have this idea of one-to-one-ness. Only one-to-one functions have inverses, and we can tell what is one-to-one by using the horizontal line test. Much like the vertical line test, it's just going to be asking the same question, but this time horizontally, and we'll kind of look at what we mean by that. I'm going to trace these functions just to make it a little bit more obvious where they are for the camera. So we have something like that. And notice that whenever we do the vertical line test on every single one of these, that it passes, right? Because there's no vertical line that touches the function more than once. But if I look at doing a horizontal line test, maybe I'll do that in my green color right here. This function definitely fails the horizontal line test, right? So we'll say no inverse because there is a horizontal line that touches at multiple points. Here, it does pass the horizontal line test, so we can say it does have, has inverse. This function has an inverse. This one does not, because if you can draw a horizontal line and it touches multiple points, that means it does not, so we'll say no inverse. And then this one does, because any horizontal line that you can draw will not touch the graph more than once. So has inverse, right? Again, just like we were thinking about determining whether an equation was in a function or not, it's easier really to look at it graphically if you have the graph available toward you, because you can just quickly scan using that horizontal or vertical line test rather for a function, okay? I'm gonna flip onto the back of this page real quick and we'll finish the last part of this notes for this section. But the last part of the notes is really just a observation on what happens with the graphs of inverse functions. A graph of the inverse function f inverse of f is the graph of f reflected about the line y is equal to x. Use the graph of the function to graph their respective inverses. So what I'm going to demonstrate here is how we can easily get the graphs of these two functions just by mirroring them over the line y is equal to x. So what I'm going to do is I'm going to draw a dashed line that is representative of y is equal to x through both of these planes real quick. I didn't do a wonderful job on that other dashed line. That's an apology there. But we have y is equal to x and y is equal to x. This is the line about which these graphs must be reflected about in order to achieve their inverse. And just to make it, again, really obvious, I'm going to outline each of these functions, again, just to make sure they pop on the camera. So we have something like that, okay? Let's look at the inverse of the first one. If I'm reflecting a line over the line, or if I'm reflecting a function rather, over the line y is equal to x, then what I need to do is I need to figure out some points that I can easily reflect over. And what I'd recommend doing is just maybe looking at where the function kind of gives you these concrete points and then just reflecting them over that line directly. What I notice here is that, excuse me, I have a point here at 0, 1. That means that I definitely am going to have a point at 1, 0, because all I'm going to be doing is swapping the x and y inputs. Here I have a point at 1, 2, which means I'm definitely going to have a point at 2, 1. Using this information, I can see that the inverse function should look something like this if I'm kind of following that same trend and thinking about reflecting all of these points across the line for it. But to get a few solid points to kind of help you get started, you can just swap the x and y inputs for them. And again, I'm going to demonstrate how I did that real quick right here. 0, 1, specifically that point right here, went to 1, 0 by swapping the x and y inputs. And then we also saw for this point right here that the point 1, 2 went to the point 2, 1 by swapping those x and y inputs. So if you want to get from a point on F that has x, y, and you want to go to a point on the inverse function, f inverse of x, all you're doing is you're swapping that input and that output, right? You turn it into in terms of yx instead of xy. So 0, 1 goes to 1, 0, and 1, 2 goes to 2, 1. We can do the same thing for this other graph that we have right here as well. And in fact, that's what we'll do. We'll pick out some important points to put on it. It looks like here I have this at 2, 0, and then I also have one at 3, 2. We can use those 2 points to get a line. If I have a point at 2, 0, that means I'm going to have a point at 0, 2. And if I have a point at 3, 2, that means I'm going to have a point at 2, 3, so right here. And you can see that if I draw a straight line connecting these guys, that I'll have something like this. And I definitely trailed off a little bit badly whenever I did this dash line right here. It should be at the point where they intersect up here, so I apologize for that. Make sure that whenever you draw your dash line that it kind of goes to the intersection of these 2 points up here, right? Other than that, that is going to be our discussion on the inverse functions, okay? Whenever we get back next week, we'll begin our Chapter 8 stuff.